I Oh my god, I just accidentally muted my mic and haven't realized that yet. Till only I just seen that. Sorry for that. I think oh my god, today is kind of you know I'm facing a lot of troubles. It's troubles with my second monitor and my power supply. Now I just turned off my mic, and I just basically talking to the mic without realizing it's in mute mode. Whew. Okay, okay, let's just all I just said is, mm, you know we are trying to implement GPT-2 in Rust, right? So the first step is, I think in our previous live, I just talked about a lot of these things, tensor engine and how model works and operation, right? So today I'm going to talk about the first part, which is a tokenizer part, and the tokenizer part is simply standing between the actual words and the model. It's basically intermediate between model and the word. Basically, go back and forth, where you are assigning unique token for each kind of word or subword in our data set, and just just completely exchange all of the words to their Unicode tokens, and take the kind of the token file and throw away the actual data, because we no longer need it. All we need is the IDs. We exchanged the IDs, like the tokens, right? So that's how it is. Just wait a minute. So this is the first part of any kind of a language model nowadays. As far as I know, this is the first part. When you are trying to implement, first you need a tokenizer. Once you have a data, you need a tokenizer. Because you need to tokenize them to some unique ID, unique tokens, so that model can understand the relationship between the, because model cannot read the actual text, right? It's all of the thing it's going to be see is a token number, right? uh, so that's why we need a tokenizer thing. I think I'm not sure what kind of I think they used some kind of byte pair encoding tokenizer or something like that for GPT-2. They have a library called tick token, where basically where basically the tokenizer, they used that for their 3.5 GPT model, and the GPT-4 as well, I think. So, but we are trying to write in Rust, right? Our implementation is based on Rust, so we cannot use that, but instead we can build on by ourselves. So for now, let's just put the part aside, the tokenizer part aside. So first we just focus on this embedding part. Then we will compare come back to that tokenization part later. For now, because why am I putting that aside is because I'm not sure about which data set going to be we are going to be used. So if we are if we are if we are going to if we are going to use the common crawl or something like that, we can use their tokenization. Basically, once you tokenize, maybe for tokenization, say tokenization part, we can just use the Python implementation. Or if we are going to train our model with some custom data set or something like that, we need a new tokenizer, right? So that one of the thing we need to keep in mind. That's why that's why I'm saying let's take care of that part later. For now, let's just dive into this embedding part, which is one of the most which is one of the core part in the transform architecture. So basically, once you have a token, right? Once you convert the word into a token, you have a token. Let's say you have the let's say let's say if a sentence called the dog is loyal to a human, then you need to convert them into a token, something like the dog. The is the unique ID of the is basically something like a 26, and dog for 30, and yes, is is for 37 or something like that. But here, you need to pay attention here, because I'm just talking about the world level token, but it's current standard, it's not like that, because nowadays most of the models are hugely rely on this chunk part of words, something like they separate the loyalty. Say they just separate the, let's say the human word human into two parts, something like a hum and an. It's a different token. HUM have a unique token, and AND have another unique token, and space also have a unique token or something like that. So it's going to be like that. So once we had it, once we convert every word into a token, then the next part, next part we need to do is that for we need to do is that we basically convert them into a vectors. So what I mean by that, vectors means basically, in a if you are came from linear algebra or something like that, you know what vector is. Vector is simply a sort of array. You can think of it as it's much deeper than that. I don't want to get really deep into the mathematics now. All I want to know is that it's kind of array. So 2D array, 3D array, 4D, 5D, some kind of a higher dimensional array. You can imagine, like you can think of it as like that way. So once now we have, let's imagine now we have a token, right? Array. So we need to assign each unique vector to we need to assign a vector to each unique tokens, right? So that, so in the end, each set of tokens going to have their unique set of vectors. Okay, it's not a set of vector, unique vector. Okay, let's say I said the word the it's let's say it's a token number 26, then it's going to be have their vector. The dimension is up to us. Okay, the dimension of the vector, it's up to us. You can set it you can set it what number you want, but there is some sort of procedure for it. How to set it up perfect and good number, so that our model can predict our model can give high amount of accuracy. uh, so that is how it works. Because when the model going to see a token, okay, it's not going to see the unique token ID. It's going to be see the according vector, the unique vector of the according token. Okay, it's going to be seen the not as id, just the id. It's going to be see the vector, each according vector to it. So that's the vector part is really important, because that's where actually the learning happens. Because once you have a vector for each set of token, so now the model can understand the relationship between the vectors. Okay, oh, this vector, something like a, if I have a word dog and the cat, so what model can understand is that it can, if I have a vector called a vector for dog and the vector for cat, now the model can easily understand that both are same animals, right? Both of them are pets animals, so both of them are kind of like important to humans. They are related to humans. So what model can think and do is that, oh, these two vectors are kind of like some sort of a relation, kind of like having some sort of a relation in between them. It's not opposite, it's not basically, it's have some closer relationship. Okay, so that it can put those vectors in the high dimensional space much closer to that, instead of putting on a dark vector in some sort of a direction, and putting cat vector in opposite direction. It's not going to be do that, because that's how the model will learn. Because the vector part is very very important. It's very very important. Without that, model is basically struggle to learn. It's not going to learn at all. Because there is no room for to model to understand the relationship between, as long as you increasing the vector dimensional size, it's going to be much beneficial for the model to learn and understand complex relationship between them. That's one of the thing. So now what we are going to do is build that build that embedding layer, so that we are just taking the raw input and assigning a set of vectors. Okay, so the actually the embedding part is not a single sort of layer. It's a two layer. It's just that for it's for unique, for each set of token, it's going to be have a unique vector associated with it. At the same time, we need to take care of this context length. Okay, so context length is basically meaning that the amount, it's kind of a RAM. You can think of it as a RAM, right? If you're using computer, you have a RAM, right? So something like a 8 or 16 or 32 or something like that. So if you're using it, let's say your RAM is 8, right? You cannot use much more than that, right? Once it filled, you cannot use much more than that. That's it. That's the limitation of your computer. So the context length is kind of like that, but now, state of the art models somehow break this bottleneck using some variety of methods. But GPT-2 GPT-2 basically have this bottleneck. So basically, what I'm saying is, the GPT-2 model only can see up to 1024 tokens. It cannot see much more than that. I mean, GPT-2 small model, which they introduced, GPT-2 small or something like that. So it's a 124 million parameter model, and it's going to be, I think it's 124 1024 something like that. So the reason, because it's going to be fixed. So is because the reason is, you have this layer called positional encoding, positional embedding. Is is it's basically for which tokens are where. Okay, let's say we have a 10, we have a sentence called the dog is very loyal to human, and you need to know the dog is the second word of the sentence and the human is the last word of the sentence. Okay, if dog appears again in your sentence, you need to understand, some sort of some sort of a dog related food, or some sort of a dog related thing. Again, in our context, the model needs to understand this dog word and the food is basically related. Okay, it's basically need to know the position of the word to understand the data very well. Okay, for that we also introducing the positional embedding. Basically, for before we have a vector for words, right? Now words are subwords. Now we are going to have vectors for each position in the context. Okay, remember, you cannot give more data than the context length. It's going to be fixed. It's going to be fixed, and it's going to be yeah, once it's fixed, and once you train the model, and once you finish that, you have a weights and you can inference it, and you cannot pass the context length. Okay, it can, sorry for the smashing mic, sorry for sorry for that. You cannot you cannot increase, you cannot give more tokens to your model. Okay, that's how it is, because once it's trained, it's going to be fixed. Okay, and the architecture is fixed, the weight is fixed, everything is fixed. So you cannot just say, you cannot just send more tokens to your model, because that's not how we train the model, because there is lots of things going on here inside of here. Okay, so that is another thing you need to keep in mind. Okay, so that's it. So now we are going to build this embedding layer. So here you can see that. So here we are just importing some sort of a library which is for generating random numbers. Okay, nothing more than that. This part is basically, we are, you know, this is our basic CRAD engine, sorry, tensor engine. Okay, I hope this all makes sense. And now here we are just creating our own stock for called embedding. Then, sorry for that, it's going to have a, okay, field of weight, size, and embedding dimension. Basically, the actual weight, actual vectors, it's going to be a matrix, right? It's going to be a matrix, and it's going to be a higher dimensional matrix. Okay, and the size, basically, the workup size. If it is for word embedding, it's going to be a workup size. If it's for positional and embedding, it's going to be a context length. Okay, and the dimension, basically, whether it's a 2D or 3D or 100 dimensional matrix, 100 dimensional vector, or a 500 dimensional vector, or a 768 dimensional vector, it's up to us. Okay, and we are implementing some methods on it. It's basically a new method for creating the actual, you know, um, actual actual matrix. So it's going to take a size and embedding size, nothing more than that. It's going to be return the self, which is this array. Okay, this struct embedding, and we are just taking this random number generator thread and total number of weights in a lookup table. So how many, um it's basically for how many numbers we are going to have in entire lookup table. Okay. um if it is a matrix, let's say we have a 2D vector and we have four of them, it's going to be a 8, right? It's going to total of, it's going to be have a 8 numbers, 8 floating numbers. Once we find that, once we have a number of weights, then what we are going to do is create actual uh, vector. So this is ranging from 0 to number of weights, which is the number of floating point number we need to create. And this map operation is basically throw away what's inside of that. It's going to be kind of like a iterator part. It's going to be generator something like a 0 to the number of weights, you know. And the map part is take the iterator and just throw away what's inside of it and putting the now here we are generating some random number between, sorry for, so here we are, you can see here we have generating random numbers between 0.5 to 0.5. So basically when it's come to whites, we basically sort of keep it very low, something like 0 points, something like that. You cannot never see a number something like a 10 or 11 or 12 or something like that, model whites. It's kind of distribution and sort of things. If you keep that number small, your model is going to be good. For now, that's all you need to know. Maybe in the future we will cover why it is. Okay. And it's going to be collect that, basically sort of, well, once you put everything, you throw away the number and putting every random number generated, and you are going to collect it. So now we have some sort of a data. So it's going to be have all the numbers we need for all the tokens to create a vector. And now we are returning the self. So actually we are returning this with the tensor. So this tensor is basically coming from our tensor engine. So now we are creating the tensor with the actual data. So you can, maybe you can, here you can see this is the method we are going to call it. We are going to put this shape and the data, nothing more than that, nothing fancy here. Okay, now we have a tensor. Okay, and the size and the embedding. Now we have a embedding. So embedding matrix, now we are actually having the embedding matrix. So let's do this. So let's, for now, for experimental purpose, we are just creating two set of variables called vocabulary size and the embedding size. And we are going to create it. Okay, we are going to create it. So that embedding, so that's it, right? So if we run this code, we can see that, just clear this cargo run. Okay, it's a cargo. Yeah, here you can see that the some sort of weights are basically printing, is because here once we created the actual matrix, word embeddings, and we are basically, so we don't need this. Basically we don't need this at all. Sort of, we don't need any of these things as we are hard coding it. So what we are saying is that Hey, so what is the size and the embedding size? Hey, I need 1,000 vectors with the dimension of 50. Okay, it's going to be a 50. It's need to be a 50, 50 dimension, 50 dimension, and it's need to be a 50 dimension, and I need thousands of vectors. Okay, that's that's all this code is doing. Okay, that once it's finished, it's going to be written the our embedding struct. Okay, so now embedding layer is embedding struct type, going to which is it's basically having the weights and the size and the embedding dimension. Okay, so now we can sort of basically printing the length, basically printing the length uh, of basically printing the length of the weights. Okay, then we are just basically printing the shape. So length, so let's just show you what it means. Sorry for the desk sound. And so this part is what we are doing is we are we are going to catch up the you know this input ideas is here we need to be careful. So what we are doing here is create some sort of array. So this is how our data going to be look like. Okay, we have a token 10, 24, and 5, and 999 and 25. Okay, this is how our data look like. Okay, then once you finish this, we need to send that, we need to send that to the embedding layer. Okay, so here you can see we have implemented some, I think I have implemented some method called forward. Okay, it's not, it's basically it's what it's going to do is take the data and return the vectors according to the according to the data. Okay, if I have a 24 25th if I have it, the token 25, it's going to be give the vector, specific vector for the token 25. Okay, if I have a token 10, it's going to be give a vector specifically for the token 10. So this tokens, this vectors is not going to be assigned to any other numbers. It's going to be if it is a 25, it's a 25 some vector that's specifically for 25, nothing more than that. It's not going to be assigned again any other numbers. Okay, so that's what it is. And let's just here we are just you know how many vectors we need to assign for. We are just taking the length and um, put it in a vector with the length and the dimension, embedding dimension, and output data with the capacity is basically meaning that we are just creating some creating a array in a memory without a vector in a memory, without initializing anything. So it's going to be a empty vector, and still it's going to be having an array. So later you can fill them all. Okay, so once you did that, then we are going to run some sort of a for loop. Yeah, it's a for loop, and it's going to be input idx. So we are taking each tokens instead of the input idx and token. And if we are just basically checking the token id is token IDs should be lower than the size. What I mean by that, if we are using this for let's say if we are using this for word embeddings, we have a vocab size, right? Vocab size. Basically, that's basically that's the possible tokens the model can predict. Okay, that is the all possible tokens the model can predict. Nothing more than that. Okay, if our vocab size is 10,000, so the model can pick any one of the token to predict inside this 10,000. It cannot predict a new token which is not in the 10,000. Okay, this is all the tokens it can predict, because this is the token it's going to be trained on. So how could it can predict a token that is not in a vocab size or a data set? Okay, it cannot simply it cannot do that. So that's why we are checking this, is because whether the token ID is in vocab. Okay, if it is larger than the vocab size, which is basically out of the vocab, here you can see that. So the token ID is out of found for the vocabulary size. Okay, that's why we are kind of if loop if here and calculate the start and end. Basically it's a relatively very simple I would say. Now what we are doing is it's relatively very simple and understandable embedding layer. Okay, so what here we are doing is we are basically calculating the start and end index. So what we are not having some sort of a lookup table. Instead what we are having is one flat array. Let's say before I said that here you can see that we are setting this to I want 100 vectors, yeah, sorry, 1,000 vectors. That should be in the dimension of 50. So if you multiply this, how much it's going to be 50,000, right? So that the so it's not going to be maintained in a matrix. Inside it's going to be in a sort of like a flat array, which is start from 1 to 50,000. Makes sense, right? So it start from a 1. It's a simpler single sort of array, start from 1 50,000. So it's if it is a single sort of array, how can you pick up a vector here? Okay, so the thing how can we can do that is let's say here let's say the vector. So the the every vector in the every vector is going to be a same length, right? So we set it as a 50, so 50 dimension. So the first 50 number is going to be a first vector. Okay, very simple, right? The next second 50 number, it's going to be a second vector. The third 50 number, it's going to be a third vector, so and so on. Okay, makes sense, right? It's going to be very simple and easy. Okay, so that's what we are doing here. It's simply we are basically doing that. We are having this one flatten array and picking the right vector. So how we can do that? So we are simply multiplying the vector token ID to the embeddings. So basically, if I have a 25th vector, okay, if I have a token 25, all I need to do is multiply with its dimension. So it's going to be in something like a 25 into 50. It's something like a 2 so how much it is? It's going to be 1,200 250, right? So it's going to be pick a number from 1,250 to 300. Okay, that's it. So that is the starting index. So we are calculating the starting index. The end index, so starting index is 1,250. The end index is 300, 1,300. Okay, because we are setting our vector to have a 50 dimension of 50. Okay, that's it. We are just adding the start index two self embeddings, which is we have here we have a 1250, and another 50 is going to be 300 1300. Okay, get the slice representing the embedded vector. Once you finish this, we need to take that. Okay, okay, now we have a start and end. Let's take the vector, actual vector. So we are grabbing this weight data, basically self dot weight data actual, where the actual the big flat vector stored. We are going to index from this to this. Okay, and once you have this stored to the embedding vector, then what we are doing is according to the output vector. Basically here you can see that we just create a where we just create the vector for it. So with the capacity of the length, once you have that, we are going to append that. Okay, now we have the output data. What we need to do is, so now we have data, so all we need to do is convert that into our tensor. uh, Wait a minute, tensor sort of thing. Just wait a minute. I will back in a minute. Okay, just forgot to do some little work. now, but so where we are now, where I just left off. Okay, okay, now, sorry for that. Oh my gosh. Sorry for that. Just find a minute. Okay, so where I left off. So once we convert this, we just sending the shape and output to the new tensor type. The another thing I wanted to point out here is that there is a lot of improvements we can do to this code. But for now, let's just leave it as it is. So let's first get it work, then we can, you know, implement, then we can optimize them, make them more efficient, sort of things. So, so at this part, at this, okay, now you can see now we have both sort of both the embedding layer and the positional embedding. So all we need, it's going to be, all we need to do is to, all we have to, sorry for that, all we have to do is to change the vectors and size. Okay, nothing more than that. So let's just delete all of this. So we need this. So the output is, you can see something like these are the vectors. So these are the vectors, this is the vector, and this is the vector for we have some tokens, right? We have this is the 10th token, and here you can see we repeated the token 25, at last, and that should be the second, that should mean that the second vector is basically, but where is the second vector? Yeah, so this should be equal to this. Yeah, both of them are identical, right? You can see that 0 0.02948, 10294, right? No, you can see that, right? So that's how it is. And now you can clearly see that it's working fine, so we don't need, let's just, what are the things, maybe we can, okay, this is a embedding layer, this is not a embedding layer, it should be a word embedding layer. Okay, then it's really hard for me to type in this way. Positional, maybe views. Then it's going to be like this, and we are just calling that new dot. So you know, here I have a struct called config. It's basically for configuration. So here you can actually, we need to config this to something like a let GPT config. Wait a minute. Sorry for that. Sorry for. Assigning all of this. GPT, there is much better way, I would say. There is much better way to do. There is should be at least some much better way to do this. But for now, it's fine. Okay. So it's going to be a block size. So the block size is going to be for GPT-2. It's going to be, which is a context length, it's going to be 1024, and the vocab size is going to be, it's going to be something like it depends on our data. For now, let's just assume it have a 10,000. Okay, for for experimental purpose. Okay, and layers is basically for how many layers we are going to have. Maybe we can take that from the actual GPT-2. Where is the data class? Oh, here you can see 12, head is equal to 12, and embedding is 768. So it's going to be 12, and head also 12, and n layer, it's not n, now it's so now we have okay, number of embedding is basically per dimension. Okay, 768, that's it. So now what we can do something like this. So how many vectors we need to have for word embedding is vocab size. Okay, and for this, in the dimension, it's simply I'm not sure we can send something like this. Let's just see, and just it's much complicated than you know. Okay, so now we have what we have here. So how many vectors we need to have is for positional embedding is block size. It's going to be a 1024 and same. The dimension is same for both of them. Okay. Now we have this. Okay, we are creating this and this. We don't need this anymore. Let's just delete this all. Do we need this? No, 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 we don't need any of those. Okay, okay. Maybe let's for checking still keep this. Okay. Then why we have some assert here output matrix that shape and the input id length and embedding size. Okay, the output should be shape should be number of inputs tokens. You can verify that too. So we don't need this. Okay, that's it. So I hope this work. So we are still sending something and printing something. Cargo run. So these are all of the errors are found in this, not found in this code. So it's not okay, okay. Sorry for that. We, I still have this sort of wide memory of the Pythonic things where it is what it is. So it's going to be Neo. I'm not I'm not really good, very good at Neo. I'm basically what just happened here. I'm basically trying to do my best because I'm learning new. I'm not expert at it. Rust also, it's not my best. Still, I'm learning Rust. Okay. Now I think still it's not working. What are the error? So let's look at the first one. We missed this and the second one GPT is stuck with a similar name exists that config. Not found in the scope. What do you mean? It's sorry for that. I'm just now now it's basically work. Right. Now it will work. Still we have those errors? No. These are actually these are not errors, these are warnings. Cannot find a value embedding layer in the scope. What do you mean by embedding layer? It's actually it's not embedding layer, it's something like a word now. Okay. Uh it's making me the reason I'm typing my typing is very slow is because I'm placing my mic and the wire is I'm placing my mic is basically in front of me and the keyboard is also in the front of me. I am placing my mic between the keyboard and me, so it's really hard for me to type. And when I get my get off basically get my hand out, I need to careful to smash the mic at the same time. The wire also mess with my hand, so that's why. So I need to find some good stand for it, so yeah, I have to do that. uh, uh, okay, unused, these are warnings. Unused, use the duplicated function, no problem for now. Duplicated match, okay, no problem. Stop that. As a no field of, no it have. Oh, sorry for that. It's actually, so we maybe we can change here. So it's actually okay, that's it. Type config, okay. Mismatched mismatched tag. Argument to be a function incorrect. Use as. What is it? It's oh, it's a I32. Okay. It should be a use size, right? User is also basically on it's kind of a dynamic thing. I32 still so use size is basically for if you are on a 64 bit, it's going to be a 64 unsigned integer. If you are on 32 bit, it's going to be that. So workup size is going to be it's going to be a measurement, right? So it's always going to be a plus sign. So maybe we can change all of them to be like use size, because I don't see these will be in a minus. There is no way. Use size. Okay, block size. Yeah, it's going to be also use size. It's kind of hard. Okay, now everything on a use size and much more clean way. And this is why this is one of the reason I why I like to read the error. See, you can here you can clearly see that what is the error, and it's mentioning everything, right? Rust compiler is one of the best thing. One of the best thing about Rust compiler is that it's pointed the error much more clear and understandable way. You can if you are programming in Python or some sort of some other language, it's going to be much harder for you to basically understand the error. It's basically pointing out some other line, but the error in some other line. It's going to be do that. It will do something like that in other set of languages, but in Rust, it's a total different story, bro. That's one of the feature I like about the Rust compiler. How much time gone since we are basically I'm not sure how much time gone. If I can pull up the OBS, I can see the how much time gone, but I'm not going to do that because it's not a pleasant to see. Maybe, maybe I'm a bit overreacting. Maybe I'm a bit caring too much about the viewers. Okay, that is what it is. So, wow, why I just cleared that? Okay, what are the other mistakes we have here? Okay, just wait a minute. What needed? When you're creating a stack, if it is going to be use, oh, it's going to be, oh, sorry for that. Oh my God, let's just put all of this like this. No, in I think in NeoVim we have some command, something like this slash and use size, you know. Then we have another slash. It's going to be just pattern not found. We do have something like this, isn't it? Just why it's not working. I don't know. Yeah, now it's okay. It takes some time to basically getting good at. Now we have. Okay. I hope you can. we do have a lot of errors. Never used, constructed, never used. These sort of things are warnings, because we are not still using them. So what are the things is anything we need to worry about? Unused, 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 never used, never used, never used, never used, constructor, never used, never used, never used. These are the things never used. Okay, still okay, now you can much more clearly that this is basically whenever you see some gaps, so this is the end of a single vector. Okay, now we have a 5 vector and a dimension of 68. So now that's it. So now we have it, right? So okay, now we have them. Okay, now we have both embeddings. Let's just change this file number to not wt. uh okay, let's just, okay, if you have anything somewhere here. We are in a normal mode, and we are in a command mode, and it's going to be slash, yes, it's going to be wt, going to be embedding, embeddings. That's it. So now that we finished our embedding part, let's go into next part. So maybe I can show you the architecture. Transform shit, there is some it's really kind of frustrating me, because you know there is some there is function happening. It's kind of a celebration thing. They are basically playing songs and dancing. I can still hear those musics. So I hope you are not hearing anything. Uh, if you are hearing something, it's going to be bad. I'm in a trouble, basically. So here you can see we have this. So once we have both two, then we need to add them. Okay, that's maybe we can if we look at his implementation, the Andre Kapati, you can see here, you can see that once he have this, here we have both embeddings, sort of thing, and say, what is it, once you have this, here we can, he basically adding them. So for our thing, we have remember what we have is not array, not a vector. It's basically um, so basically, yeah, our custom tensor data type. So we can we add something like this, what he call this x, let's say call this as x, and adding both word embedding. Can we do this? Positional embedding. So it's not actually, okay, it's going to be a vector. So it's need to be, we need to add the data. So it's not a, okay, can we do this? I hope I afraid we are not. Let's just run this code. huge amount of. He cannot basically. Where is the error? So not found in this scope. So, oh, did we add them? I thought we need to implement some sort of a trade or need to implement some sort of method for it. Interesting. Where is this thing come from? Basically, forward that word. Okay. Sorry for that. So we are creating it, and the forwarders were basically picking the vector. So here we are just only picking them. So we are just, so all we need to do is, okay, let's just okay, we are sending this, and let's just out, output. There is must be a much better way to do this, but for now let's just make this thing work, then we can make it more efficient or something. Okay, it is. And once you, okay, now we have this both, all we need to do is we need to let so for that x equal to output, so it's output dot word plus and output dot, okay, that's it. So but still it should be a data. Okay, not found. Let's just try this. Maybe x dot, it's still going to be a tensor, is it? Do you think it will work? No. So after all, we cannot do this. Cannot add. Oh, this is the problem. So it's both of them going to be a VEC F32, even though. But how we can add this? Let's just ask our. Here we have a. Yeah, yeah. That's exactly what I thought. We need to implement some sort of a trade or some sort of a add method in it. Okay. So how we can do that? So all we need to do, come here. Sorry. Um, Come here. Fn. So basically add. So here basically it, need to take two set of array. Okay. So maybe we can just take the self and the another array. It's going to be let's say called as another what we can call this as let's say call this as a b. Okay, it's going to be vec I32. It's not I32, is it? F32. Then all we need to do is once we got this, so what we are going to return, we are going to return the same thing, tensor. Maybe we can self. Okay, and then so how we can add this, how we can add those. Okay, is there any function, is there anything, any sort of inbuilt method for it? Let's ask, sir, is there any method that for to, sorry for that, why am I typing everything in a reversed manner, for to add the to vec f32 f32 and rust. Okay. Oh, so iter zip and b iter and map, incorrect. Okay, our so the thing I just made a mistake. Okay. Let's just for now let's just follow this. but maybe we can follow this method instead. Actually, what I just did is that I'm setting this to basically setting this to block size, right? That's not actually what we want here, is it? Still okay. Oh, okay, no problem. Why am I sorry for that? I'm just basically confusing myself. So how we can add this? We can use this standard thing, trade, optional custom trade. If you want to work directly, you can implement this trade where implement for vector type k. Hmm. Maybe we can just do this. Okay, where just implement this vector. Maybe I just use this. It's what is it? std ops add. So it's going to be like this, and we just need to implement this here. So this thing is basically for this thing is basically for compiler sort of thing. It's kind of a metadata thing. I'm not quite good at that yet. As far as I know, it's kind of a metadata. Okay, here we just implemented that. Okay, now we can do this. I think we can do this. I'm not sure. Importing, so maybe we need to do this in a main function instead of this. Let's just try this way, and clear. um Still we have that problem. Okay, only trade defined in the current CRAD. Only trade defined in the current CRAD can be implemented for type defined outside of the CRAD. Okay, what is the problem? Vec is not defined in the. Okay, this should be defined in the main file. Okay, that's what I'm expecting. So we need to define this. Let's just okay, delete this and put it in a main file somewhere. Maybe we can put it here. Okay, let's just see this. Oh, see this. Still we have. Didn't I save that file? Yes, I just. Sorry for the smashing. It's still kind of hard. Come on, what is the error again? So these are the others are Okay, where did this happen? Did I deleted it before? I don't have any sort of memory in deleting that. It's a number of embedding. It's not. It's a block size. Okay, that's what it is. And implementing tensor. Okay, so we just left this. Oh, there is a lot of errors. These are unused things, so we don't need to worry about. Still, we have this. Now I'm pretty sure we will not have that here. Go Tatra. Why am I having this again? Hmm? Only trait defined in the current CAD can be implemented for the type. It's outside of the CAD. What it mean? Vec is not defined in the current. Okay, okay, like that's why I just put it in the. Actually, where we define the vec, we are not defining the vec, but we are using the vec in our tensor definition, right? Let's just ask GPT. So we need to um here I have this custom stack. So this data field is what I need to add. I need to add basically there is something like a dot data plus b dot data. On this, how can I define that trade? So how here defining that? Sort of we are defining add trade for tensor itself. Okay, interesting. Implement trade type output is equal to tensor. Sorry for that. Okay, output is equal to be output is going to be a tensor, and assume maybe we can set it as a self here. That just basically working. That will also work fine. This is how the addition is. Okay, I'll just copy this. So this is the thing, and then we can just add something like this. So the okay, that's it. So let's put it here. Okay, yeah, basically implement. How much time is it? Are we crossing the Okay, let's just run this. Still, we have some sort of error. Actually, we just forgot to delete this. And okay, oh here seems everything. So what it actually saying is that shit, shit. Oh, it's there is when I'm using VS Code, I can see there is a lot of basically unwanted behaviors. Sort of say it happens a lot. Even you can see that now and before we have there is some sort of others. It's basically I don't know why it is the case, but I do have sometimes experienced this. Okay, now how much lower not found in this course scope. So mm, okay, we need to use this. It's a yes dd ops and add. It is so now still we have the oh my gosh, if somebody in my lab watching this, I'm sure they will going to be frustrated watching this is because I'm back and forth with this loop, man. The reason because I'm not still good at Rust yet. That is why. But pretty soon we'll be there. there is a lot of other errors which we don't want to deal. So these never used Amna. I I I should find a way to avoid these errors because it's always coming and kind of bothering me. Yo, yeah, I think we did it. Did we cross? I think we did it. So so now we did that board. Okay. Now all we need to do is fed this to a model. So it's GPT start. So let's we have this. We have here. So next what we need to do is something like it's going to be written a hutch. Maybe call it as a hutch. Let hutch equal to so going to be what do we call this is a GPT2 dot forward or something like that. Let's just see. We have a token embeddings, positional embeddings, and block, and yeah. So we don't need this. Why we need this? Wait a minute. So it's a sequence. If we call forward in it, it's going to take a self and input, which is a use size array, and return a tensor where it's adding. We are adding them. Sort of like we are im- are we implementing our own embeddings here? Oh my gosh. Just see how much we just Okay, so here we are taking the GPT and input ideas. Okay, so here we are already implemented another set of um, yeah, buttons. 10 states, tensor.0, and the sequence length and the number of embeddings for I, and enumerate them, index and the tokens, and let. Okay, here we are creating a offset basically for token embeddings in the dimension and the positional embeddings I, and the dimension. And it's kind of a where is the matrix for J and embeddings? So we are going, so hidden state data I int plus. Okay, so self dot, so token embedding data, where it is coming from. Hmm. So it does implement some part of it, some part of the embedding layer, but it's not actually. It's kind of it's what it's doing. It's basically indexing the vector from the matrix. Here you can see that self token dot embeddings. It's these two things is basically the total token embedding matrix and the positional embedding matrix, and we are basically, you know, we are basically just indexing them, then adding them each element by element, then put it in a hidden state, and hidden state is I int um, I is sort of a higher lobe, and it's going to be filled the each token. Let's say have a I is equal to 1, it's going to be add them and fill the first vector, and when I change, so I, so you can imagine something like I into size plus j. It's basically, if you are processing in a first vector and I is equal to 1, and the j is representing each element in it, so you are adding and putting 1 2 3 4 5. Let's say you have a vector length of 8, then I jump to 2, so let's we start 9 at a position of 9 and adding element again. So I think we don't need this part because we already did that in this file where we implemented the add trade. All we need to do is to just remove this part from here, because we don't need this, because because we already have this hx, so we don't need it. Before we deleting this, let's pass through all the transformer block hidden state. Let's just comment this out. Do we need this? No. This one? I think no. Okay. And now that we have this, so it's we don't need this. Okay. Block and finally that thing. Okay. Now we can just so we can do something like alt x equal to clear tensor. So now that x can call, so that x can call this. Okay. Delete this. It's going to be written a tensor. Okay. So it's going to be and it's going to be an self, so it's going to be an self dot self dot data, right? And then the blocks, so maybe we can just do something like this. F n dot new, it's going to take it's going to take a x and where to be maybe block blocks. It's really does not actually, that is not what we want. So number of blocks, so so mm, we cannot create like this. I think okay. Okay, for now I think we are crossing the time for today. Maybe we can wrap things up for today. Tomorrow we are going to continue this implementation Yeah, yeah. Tomorrow we will come no continue this implementation again, and I hope you learn something. And if you watch a stream, do subscribe, like, share with your friends if you want, and I'm highly appreciate it if you did. And thank you for watching, and we will keep better and better, and one day we will very good become good at something.